I would like to start my presentation with a small experience that I had when I submitted a previous paper. The reviewer said that the term heavy metal is more similar to the term in music, like a heavy metal band, and it should not be used in defense of environmental sciences. So I have like a rebuttal written to him, and there were like 1 or 2 revisions, and then ultimately we both decided that, okay, we can use the term heavy metal. However, one thing that we have no issue is this, that heavy metals are toxic. They induce deleterious impact on the environmental compartment. They induce problems to the different environmental matrices. So I don't know how he had some mercy on me and he accepted the paper, so it's online. Yet, the problem associated with the heavy metal is this, that the xenobiotic concentration of these compounds in the environment induce deleterious impact, as we discussed, to the ecosystem. There are numerous ways to reduce the mobility of heavy metal in the environment. One of them is the use of plant and associated organisms of microorganisms, which are known as phytoremediation. And like phytoremediation can be used for a number of purposes, but then again, there is associated problems of phytoremediations as well. For instance, to apply phytoremediation at the commercial scale, you need to know the insights of phytoremediation. The most important player in phytoremediations are the plants. So you need to know the intrinsic plants that are living in a particular area, having the capacity to remove contaminants, having the capacity to tolerate the contaminants, and to grow and to promote the phytoremediation potential. So in this perspective, it is highly important that first you should have a specific pool of plants that we can use for the phytoremediation things. And then again, the selection, as I said, is most important. So after the selection, we still need to do certain probing. For example, you know that these plants can remediate a particular metal, but when you go to the field, you always see heterogeneous contamination. For example, a site contaminated with lead could have other contaminants in there. A site contaminated with TPHS could have other contaminants. So you need to know the off-site information that when you are utilizing this phytoremediation, it could be implemented to the scale. So based on this, we have like 4 scales of phytoremediation application in the field, and at this point of time, we are working on the initial site assessment and off-site testing and pilot scale optimization. From where we started? We started using 10 plants, which were really famous for doing phytoremediation. You can see the plants there: Caris raparia, Cypress longus, Cypress rotundus, Lithium salicaria, Juncus ephesus, Mentha aquatica, Phragmitis australis, Typha angustifolia, and so on forth. So many Latin words, sorry. So these 10 plants were being exposed to the polluted water, which was extracted from a site, which was decommissioned from a machinery park, and we used the water which is containing high level of metal, and we exposed these plants for 15 days, and after 15 days we discovered that among these 10 plants, only 3 were doing pretty well, which were Typha angustifolia, Cypress haloscoenus, and Phragmitis australis. So we used these 3 plants for the next experiment, and we studied what is happening when we change the hydraulic retention time. When we expose the plant to a hydraulic retention time of 8 days, we discovered there is an increased fluctuation in the environmental, in the physical, in the biochemical parameter. Just for the site, just for the, for your understanding, you can see there are 3 graphs on the top side, which were related to the catalase activity, protein content, and the ascorbate peroxidase. And in the first 3 graphs, you can see there were like high fluctuation between the control and between the polluted water. So when we grow the plants in the polluted condition, they showed the fluctuation, which is indicating the stress on the plant. But the second part of the picture indicate that when we increase the hydraulic retention time, the fluctuation was comparatively less. So this gives us an idea that, okay, if we will going to use these 3 plants, we need to have a hydraulic retention time which is at least 15 days or more than that. So at this point of time, we did an experiment in which we exposed the plant again with the hydraulic retention time of specified interval, for example, 15 days and 30 days, and we exposed them to the polluted water, and these 3 different plants were exposed to the contaminants. The system that we used was of 4 liter, and this 4 liter was comparatively bigger than the mesocosm experiment that we conducted previously, which was like 1 liter, and we discovered that using these plants, we can remove a lot of metals, we can remove a lot of pollutants, yet the story was a little complex. For instance, if we see the nutrient that we analyzed, we discovered that the incremented nutrients or incremented nitrates were observed when we exposed the plant to the heavy metal contaminated polluted groundwater. In terms of ammonia, in terms of phosphate, we didn't see any significant variation in the data. It could be because of the deposition of these compounds onto the mattress that we use, which was like gravel. However, there are like other possibilities that we need to analyze. Still not sure about this biochemistry, the chemical things. One thing that we observed was this, that the water was reduced. The water content of heavy metal was frequently, abruptly removed. The two metals that we observed not removing was zinc and nickel. And you can also see with the passage of, with the different regime of exposure, with the different hydraulic retention time, a slower hydraulic retention time, which is of 30 days, indicate higher removal of the contaminants. This story looks really nice, but when we see the toxicological profile reference to the aquatic microorganism vibrofishery, we discovered that using different type of plants resulted in different type of toxicology. So you can see here there are different lines. The green lines indicate the controls of the plants. The orange line indicates the plants when they are growing in a polluted environment. The red line indicates the negative control, while the blue line indicate a negative control, which will show the gradual degradation. So in this, only two plants were performing well, which was Typha angustifolia and Phragmitis australis. But when we further reduce the flow of the water, or we increase the hydraulic retention time, we discovered that even Syrpus halosquinus can reduce the toxicology of the polluted, not the polluted, the heavy metals in the water condition. So based on this, we concluded that two plants, Syrpus halosquinus, because it removes a lot of metal, and Phragmitis australis, because it removes metal and also reduces the pollutant from the water, are quite a good choice to be used for the upscale model. We identified that using a slower HRT, or reducing the flow rate of the flux of the water, you can remove more metal, because plants has more time to remove metal from the environmental matters, whatever it is. It could be soil, it could be water. And based on this, we constructed two different pilots. The first pilot, which is operational at this point of time, is treating 8 liters of water per week, and it is operational with Phragmitis australis and Syrpus halosquinus, and this is the diagram. It's very simple. We just feed it with 8 liters of water and recirculate it and leave it like this for the whole week, and then we analyze the water, and we are seeing that the metal are removed, the nutrient content are also very reduced. In case if you have higher amount of heavy metal which can be toxic to these plants, we are coming up with another technology, which is integration of bioelectrochemical system along with phytoremediation. This bioelectrochemical system is being prepared by Letat, which is a partner in the Greener project with us, and they constructed a 5-chamber reactor in which they perform bioelectrochemical processes, for instance, microbial fuel cell activity and microbial electrochemical cell activity, and then remove the metal and also recover certain metal, for instance, nickel and copper, and then the remaining exhausted analyte and the catholite used to go into the constructed wetland to further reduce the problem associated with the higher pH. That's a small thing that I wanted to share with you, and I would like to thank the European Commission for funding 2 projects, which are also the funder of this presentation. For that, I'm in front of you, Greener and Biosysmo. I really wanted to thank all the friends who really helped me out, like bringing a glass of water while I'm tired, or maybe helping me out when I'm really sad and talking to my mom. I also wanted to show a small picture here, which was taken by Voyager 1. Voyager 1 was a mission back in sometime NASA sent. This picture was taken at the end of our solar system, and this small blue dot indicates the Earth that we live in. And this is the small blue planet that we had in the whole solar system, in the whole multiverse, yet we are still not caring for it. So people like you and people like me are the ones who are the true warriors, and we have to think for the novel solutions. Thank you.